Why reality prefers probabilities. For a long time, certainty felt like the goal. If the laws were known, outcomes should follow. Prediction was supposed to end doubt. But physics uncovered a quieter preference. Reality does not commit to exact outcomes. It commits to probabilities. And it does so not out of weakness, but out of necessity. This was not a limitation imposed by measurement and precision or incomplete information. It was a fundamental characteristic of how nature operates at its deepest levels. The universe exhibited genuine indeterminacy, a built-in openness that could not be eliminated through better instruments or more careful analysis. To understand why this matters today, we need to revisit how determinism earned trust. Classical physics promised perfect foresight. Given enough information, the future could be calculated with precision. Uncertainty was treated as a temporary inconvenience. Newton's laws demonstrated that knowing positions and velocities completely determined all future motion. Planetary orbits could be predicted centuries in advance. Engineering calculations yielded exact results. This success created powerful expectations that the universe was fundamentally deterministic, that randomness only reflected ignorance about underlying conditions that were themselves perfectly definite. This belief shaped expectations. Better data would mean better control. Randomness would shrink. Probability would disappear. The universe would reveal a single, inevitable path. Scientists assumed that probability was merely a practical tool for managing incomplete information, not a description of reality itself. With sufficient knowledge and computational power, they believed every outcome could be predicted with certainty. The role of probability was expected to diminish as science progressed. But at fundamental scales, that promise collapsed. Even when every measurable condition was fixed, outcomes varied. The same setup produced different results, not because of error, but because reality refused to choose in advance. When physicists fired identical electrons through identical apparatus under identical conditions, they obtained different outcomes. Single photons passing through beam splitters chose different paths randomly. Radioactive atoms decayed at unpredictable moments. The randomness persisted no matter how carefully experiments were controlled. At first, this was treated as a failure of knowledge. Something hidden must be influencing events. A deeper layer must exist beneath probability. But every attempt to restore certainty failed. The randomness remained, precise and unavoidable. Scientists proposed hidden variables, unobserved properties that would restore determinism if only they could be measured. But experiments testing these proposals consistently found that no local hidden variables could reproduce quantum predictions. The randomness was not hiding determinism beneath it. It was fundamental, this force of reversal. Probability was not covering ignorance. It was describing reality exactly as it is. The universe was not undecided because it lacked rules. It was undecided because its rules allowed multiple outcomes. Quantum mechanics provided perfectly precise mathematical laws, yet those laws described probabilities rather than certainties. The wave function evolved deterministically, but when measured it yielded random results governed by probabilistic rules. This was not a deficiency in the theory, but an accurate reflection of nature's character. And once that was accepted, certainty stopped looking like truth, and probability began to look like the universe's preferred language. The shift was profound. Probability was elevated from a practical convenience to a fundamental feature of physical law. Nature spoke in likelihoods, not certainties, and this was not a shortcoming but simply how reality worked. At first, physicists tried to rescue certainty by redefining it. Maybe probabilities only reflected hidden details too small to detect. Maybe outcomes were fixed but obscured. The universe, they hoped, was still deterministic beneath the surface. Einstein famously resisted probabilistic interpretations, insisting that God does not play dice. Many shared his hope that quantum mechanics was incomplete, that a deeper deterministic theory would eventually be discovered beneath the probabilistic facade. But experiment after experiment erased that hope. No hidden variables restored predictability. No refinement collapsed probability into certainty. Even with complete control over initial conditions, results refused to settle into a single outcome. Bell's theorem and subsequent experiments demonstrated that no local realistic theory could reproduce quantum predictions. The universe genuinely exhibited irreducible randomness. Tests closed every loophole, eliminating all escape routes that might preserve determinism. This created a deep conflict with intuition. Laws were supposed to dictate what happens, not how often something happens. Rules were meant to command reality, not suggest it. Yet physics was revealing laws that spoke in likelihoods, not absolutes. The fundamental equations of quantum mechanics specified probability amplitudes, whose squares gave probabilities of outcomes. The laws were precise and deterministic at the level of probabilities, but irreducibly random at the level of events. This violated deeply held assumptions about what laws should do. As this understanding matured, probability stopped being a weakness. It became structure. The universe was not indecisive. It was flexible. It allowed multiple futures to coexist until interaction forced resolution. The probabilistic character of quantum mechanics was not chaos, but a sophisticated form of order. Outcomes were random, but governed by precise mathematical rules. The randomness had structure. It produced specific statistical distributions that could be predicted exactly. Emotionally, this was unsettling. Humans crave definite answers. We want causes to produce effects reliably. But the universe was offering something colder and more precise. It promised consistency of distributions, not of events. Individual outcomes remained unpredictable, but statistical patterns were completely reliable. Run an experiment once and the result was random. Run it 1,000,000 times and the distribution of results matched predictions perfectly. This statistical determinism was different from the event-level determinism that intuition demanded. This reframed prediction entirely. Success was no longer guessing the next outcome. It was predicting patterns across many outcomes. Physics shifted from forecasting events to mapping possibilities. Scientists learned to make predictions about probability distributions rather than individual results. This required adjusting expectations about what could be known and what science could achieve. Precision shifted from predicting particular outcomes to predicting their relative frequencies. By this point, probability was no longer a temporary crutch. It was a permanent feature. The universe was not hiding certainty. It had replaced it with something more general. Probabilistic laws were not approximations awaiting completion, but fundamental descriptions of nature. The search for underlying determinism was abandoned as physicists accepted that quantum indeterminacy represented reality's actual character. The conflict sharpened when physicists realized that probability was doing real work. It was not describing ignorance layered on top of certainty. It was enforcing limits on what could exist at all. Quantum mechanics imposed constraints through probabilistic rules that had no deterministic equivalent. The uncertainty principle set fundamental bounds on what could be known simultaneously. Probability was not a veil over determinism, but a mechanism enforcing consistency and preventing contradictions. Certain outcomes were not just unlikely. They were forbidden. Others were guaranteed only in aggregate. The universe allowed freedom at the level of events, but imposed order at the level of statistics. Individual futures were flexible. Collective behavior was rigid. While single measurements yielded random results, ensembles of measurements exhibited perfect regularity. This combination of individual randomness and collective order characterized quantum systems at all scales. This buildup revealed a subtle trade-off. Determinism fixes outcomes but limits possibility. Probability preserves structure while allowing variation. The universe chose the second option. It protected stability without sacrificing openness. A deterministic universe would be inflexible, unable to adapt or explore different possibilities. Probability provided a mechanism for maintaining lawful behavior while permitting the flexibility necessary for complex dynamics. The universe could be both orderly and adaptable because its order was statistical rather than absolute. As this idea settled, it explained puzzles that once seemed unrelated. Why atoms are stable despite constant motion. Why systems fluctuate yet remain predictable. Why noise can coexist with precision. Probability was not eroding order. It was supporting it. Quantum mechanics explained atomic stability through probabilistic energy levels. Statistical mechanics showed how macroscopic regularity emerged from microscopic randomness. In every case, probability enabled rather than undermined order. Emotionally, this was difficult to accept. Probability feels like uncertainty, and uncertainty feels like weakness. But physics was showing the opposite. Probability is how the universe remains adaptable without collapsing into chaos. The flexibility provided by probabilistic laws allowed systems to respond to perturbations, to explore different states, to maintain stability through fluctuation rather than rigidity. What appeared as weakness was actually strength. By this point, it was clear that certainty would have been brittle. A universe locked into exact outcomes would be fragile. One mistake would propagate forever. Probability allowed correction, resilience, and recovery. Systems with probabilistic dynamics could self-correct through averaging over many events. Errors in individual outcomes did not accumulate catastrophically because statistical regularities reasserted themselves. The flexibility of probability provided robustness that strict determinism could not match. The universe did not abandon certainty by accident. It replaced it with something stronger. Probabilistic laws were not a compromise, but an improvement. They provided the structure necessary for reliable patterns while maintaining the openness necessary for complex dynamics. This was not nature's limitation, but nature's solution to the problem of maintaining order in a dynamic universe. The climax of this story is a reframing that still feels uncomfortable. Reality prefers probabilities because certainty would make it fragile. The universe chose statistical order over event-level determinism because this choice enabled resilience, adaptability, and emergence of complexity. Once this is understood, probability stops looking like a compromise. It becomes a design principle. The universe does not lock itself into single outcomes. It maintains structure by allowing variation, stability by allowing fluctuation. This principle operates at every scale. Quantum systems explore multiple possibilities before measurement. Thermodynamic systems maintain equilibrium through constant fluctuations. Biological systems adapt through variation and selection. Everywhere, probabilistic mechanisms generate robust order. This insight reshaped how laws are interpreted. They do not dictate events. They shape landscapes of possibility. Within those landscapes, outcomes emerge through interaction, not command. Reality remains lawful without being rigid. Physical laws specify what can happen and with what probability, but they do not predetermine which possibility will be realized. This leaves room for genuine novelty while maintaining consistency and predictability at the appropriate level. More deeply, it reshapes humility. Prediction is not about control. It is about understanding distributions. Mastery does not mean knowing what will happen next. It means knowing what can happen and how often. Science learned to embrace statistical thinking, recognizing that probabilistic knowledge is complete knowledge at the quantum level, not a placeholder for something better. The limitations on prediction are not practical obstacles to be overcome, but fundamental features of nature. Today, this probabilistic structure quietly governs everything from particle physics to climate models. Noise does not signal failure. It signals flexibility. The universe survives because it does not insist on certainty. Quantum computing exploits probabilistic superposition. Climate science predicts probability distributions rather than exact outcomes. Financial models describe risk through probabilities. In every domain, recognizing probability as fundamental rather than provisional has enabled better understanding and more powerful applications. Why reality prefers probabilities is not a story about ignorance. It is a story about resilience. The universe chose openness over rigidity, patterns over prescriptions, and possibility over inevitability. This choice made the cosmos more adaptable, more robust, more capable of supporting complexity. A deterministic universe might be conceptually simpler, but it would be dynamically poorer. Probability enriches rather than impoverishes reality. And once that choice is seen clearly, probability stops feeling like a flaw and starts feeling like the reason anything works at all. The flexibility provides allows the universe to maintain order while exploring possibilities, to be lawful while remaining creative, to exhibit both stability and change. Probability is not what prevents us from fully understanding nature. It is what allows nature to function as it does. Why